Hey, look, it's me back there. Can you guys see me? I can't see you. You're all a bright fog. So, I'm not going to talk to you today about Clojure or Datomic or ClojureScript or logic programming or functional programming or any of those things. Instead, I'm going to share with you a message that my company wouldn't want me to share with you, and that your bosses probably wouldn't want me to share with you either. And it's about making yourself indispensable in your job. And the idea is, just imagine where you are in a software system. You're one little dot, and the systems that you build and the code that you write is eventually going to interact with all those other little dots. And the objective here, as a developer, is to make your code complicated. Not complicated in such a way that somebody would just trivially look at it and go, oh, he's an idiot or she's an idiot. But complicated in such a way that the complexity floats downstream and upstream from you and makes the things around you more difficult to manage. And what this creates is a knot of application, not just your code, but around you, that only you can handle. And so just remember, it's all about me. Right? Narcissistic design is about being narcissistic in two senses. One sense is you should really only think about yourself and what's good for you. But secondly, as a design principle, you should ask yourself, is everything going okay in my process? If I'm using my favorite language and my favorite tools and my tool chain that I like, everybody else can go fly a kite. Now, you cannot be too obvious with this. I didn't laugh the first time I saw this code, but I woke up at night laughing about this code. You can't be this obvious. The good news is that you can write buzzwords, standards compliant code that is an awful, complicated mess. And you can do it in such a way that people will look at you and say, oh, there's a hero. There's somebody doing it right. So I want to give you some ideas. The first one is to embrace setter methods. Setter methods are one of the worst catastrophes we have going, and everybody agrees you should do them, almost, so no one's going to get mad at you for doing this. But let's think about OO for a minute. OO does a couple of really awesome things, and I'm going to talk particularly about OO in Java, because a lot of people code in Java, but most of what I'm going to say is applicable elsewhere. So one of the things that it does is it gives you this wonderful separation of interface and implementation. So you have the iFly interface, and you can then say that airplanes can fly, and ducks can fly, and poodles can fly. Notice that it doesn't say anything about whether or not your statements are correct, but it does, in fact, let you make these claims. And this creates a great ability to create separation in systems, because I talk to the iFly interface, and I don't know that you're flinging poodles around as opposed to ducks or whatever. The second thing that OO does that's just incredibly fantastic, and this was to some degree really first hammered down by the Java memory model, is that it creates this beautiful red line at the end of the constructor. Right? When your constructor returns, you are published. And if you go and read the JVM spec, you'll read about being objects published. And so the idea here is it's a collaboration between you as the developer. You write constructors that make objects and put them into a good state. And then there's a moment. There's not that many places in Java where we talk about a model of time, but there's this moment in time at the end of your constructor where everything is good. And then along come setter methods, right? As soon as you start writing setter methods, things are no longer good because the constructor is no longer there. It's not making sure that everything is in a valid state. And setters do not just undermine constructors, but they also undermine interfaces. Because if I implement an interface and I depend on some object inside of me that has a setter, maybe if that object is set to some other value, I no longer implement that interface correctly. And you can make a superficial argument that you could get around this. Oh, you know what? We'll have all of our setters be constructor-like, and they'll all call whatever internal validations that our object has. But imagine that you're actually building a system. You have more than one object, and in particular, you're in the circle here that says, help! And you're asking, are the things underneath me in a sound state? And will they remain in a sound state over time? If any of those red arrows exist, the answer is no. Right? If any of those red arrows, if there are any outbound references to objects anywhere inside this graph, then I can't know whether or not the guy who's looking for help is in a good state. If there are any references to containers that contain any of these objects, I can't know. If there's any internal references between these objects, I can't know. And from the point of view of somebody who's trying to make a system complicated, this is fantastic, right? It is impossible to reason about these settable objects when they're composed. Great. This one doesn't really require any thought. It doesn't really require any justification. Everybody's going to think you're doing the right thing anyway. No problem. Now, here's one that's a little bit harder because some people are out there setting a good example and we got to stop them. You really should always prefer APIs over data. And I'm going to show you an example of getting this right and wrong from the same team, the team that created JUnit. So here's them getting it right. And pardon me for showing a screen with XML on it and using the word right in a sentence. But there is an XML format that describes the result of a JUnit test. And this forces decoupling. Right? This forces decoupling in every way. Because it's an XML format that's produced and then handed off later, it's temporally decoupled. JUnit doesn't have to be running for me to look at this report. It's language decoupled. What language do I have to speak to be able to read this report? Just XML. If, on the other hand, I went through an API, I'd be temporally coupled. I'd have to be talking to it. I'd have to be speaking that language. The XML report is effectively immutable once it's made, so people can build things on it. And what we want to do is avoid that at all costs and do these things instead. So we want to be temporally coupled to things. We want to have to write in the same language as the person we're talking to. And we want to mutate things. So now, looking at JUnit again, here's them doing a really nice job. Right? Here you go. Now we have something that is plainly data. Right? Setting up a test suite, specifying that A, B, C, and D are in a test suite together. But oh no, it couldn't just be data. We're going to make some classes and some interfaces, and the comment is just fantastic, right? If you read the comment, this class remains empty, used only as a holder for the above annotations. We know we're doing some good complexity when you find yourself having to say things like that. So JUnit, unfortunately, isn't as complex as it could be. If we could get rid of that XML report, that would be a help. If we could force, for their example, to be a callback API, in order for you to get that report instead of XML, that would be an improvement. But APIs are not really the limit. Even better than offering people APIs is offering them a DSL. Nothing says screw you like a DSL. And this would be good design, right? Good design would be a big, solid information model upon which we maybe build an API, upon which we maybe have a nice DSL. Don't do this. You want this. You want to build a DSL, and then when somebody can't use it, maybe get forced into backfilling an API, and if at all possible, never, ever, ever have or document an information model. This pattern, by the way, also goes really good with a documentation pattern of only document via like Stack Overflow questions. Right? So people learn how to use this only by example and would never even suspect that there could be an information model underneath. There's only sort of an interactive QA process whereby you find out how to use it. And the beautiful example of nailing this, absolutely hitting it out of the park, is of course SQL. SQL is an amazingly powerful DSL under which there is no API or information model that you're allowed to get to. It's never been specified. It doesn't exist. Fantastic. So if you want to build things out of SQL, what do you have to do? Mash strings together. Is that a problem? We want to put our downstream users in the same position that SQL put us in. Right? Give them a DSL. Do not give them an API. And by all means, do not give them an information model. Now, here's an example of, unfortunately, making things nice and simple. This is the kind of thing you want to avoid. The JVM class file format actually is an information model. It specifies in data what Java classes look like. And it specifies, and almost all the time, these things are treated immutably. Not always, but classes are mostly treated immutably. So this is a wonderful, wonderful point of simplicity for leverage and reuse. Don't make things like this. Now, if you are forced to make things like this, though, when you do get a chance to program against it, you can muck it all up with a nice immutable API with getters and setters. So, one of the great things about these things is you can combine them, right? If you're thwarted at one point, they gave me a good information model, you can go back and screw it up by having a nice immutable model on top of that. Always connect. Never, ever, ever in queue. Don't even ask this question. And this is what OO is fantastic for, because OO just presumes everything's connected to everything else, right? I've got an object which has a reference to an object, which has a reference to an object. Do not ask any questions about what the other dots in your architecture might be doing. And never, ever, my coworker, Tim Ewald, always goes through diagrams like this and draws a line through every one of these connections and says, what happens if this breaks? What happens if this breaks? Don't do that, right? Just go, right? It's not broken right now. Just go, assume that everything is connected. Because connected OO is the tightest kind of coupling that there is. You can presume that objects are available and close. Now, my goal would be to have you never make a queue. If you're trying to make things complicated, queues are an abomination to be avoided. But if you are forced to make a queue, hide it behind an API and make that API look like you're just calling methods, right? Because then you can trick people into doing the wrong thing. And again, people do this all the time. So also, it's not nearly as good because it's really getting pretty much towards simple. But if you really are forced to make a queue and kind of make it visible, you can still hide it a little bit with actors. That doesn't hide it nearly as much as I would like. Actors are dangerously close to being simple and useful, so I would be careful about that. Much preferable to use OO where possible. Now, here's a biggie. Create abstractions for information. Right? Every time you have a piece of information that you have that's new, you need to make up new interfaces to get to it. Right? In Java, this is typically called Java beans. The fact of the matter is that information comes in a few basic shapes. Information comes as scalars of different kinds, numbers, Booleans, characters. It comes in sequences of those. It comes in arrays. It comes in maps. And it comes in sets. But do not ever expose information this way. Because if you expose information this way, then other people already have collection libraries that you can use to manipulate that. You don't want to do that. You've got to screw those guys. You've got to actually make a bean, customer bean and order bean and all these things for which there is no extant API, and then they have to make an API. So encapsulate. Encapsulation is the complexity lover's friend. In particular, make sure people can never get access. We've kind of already covered setters. They got their own bullet point, but let's focus on getters. Make sure people cannot get to the raw fact that they have associative data or that they have a set of data. They've got to go through beans. Your code base will automatically become an order of magnitude larger. Right there. Boom. And this is how we work already. So again, you're not going to be harmed. And the best part about it is, the only argument for this is that it protects you from change. But information itself is already an abstraction. Right? Sequences, maps, all those things, they're already an abstraction over what's going on underneath. So if you're going to play that game, I encapsulated to protect me from change, there's no point in stopping at one. I mean, why not encapsulate the encapsulations in case those change? And if you're going to do that, why not you encapsulate the encapsulations of the encapsulations? Right? There's absolutely no limit to the opportunity there. Now, people are likely to figure you out if you do that. So you might want to stick to just the one that's the industry standard, instead of additional ones. Now, here's a really good one. Use static typing across subsystem boundaries. The across subsystem boundaries is important. So imagine back on our picture here, we have the little red guy who's going to produce some data and the little blue guy who's eventually going to consume some data. And there are a lot of intermediaries in between that don't care about the data at all until you add static typing to the mix. So the game here is to see how many intermediaries you can break. And so the goal, and think about it, because everybody's going to agree with you, right? You can say, look, if you're in a statically typed language already, you can easily say, look, I'm being very rigorous here. I'm specifying exactly what I'm doing so that we don't have any bugs in our system. And you specify it so exactly that every intermediary has to know about it or they will fall over. Now, You can do this with data, but an even more beautiful way to do it is to do it with errors. And so the patterns here, there are a number of them, and they all work by themselves, but you can use them together. Use checked exceptions, right? That makes puts it in everybody's face. Use lots of different exception types. Look, we've thought through error handling really carefully. We've documented 50 different things that can go wrong, of which the only mitigation strategy is you give up. But we've made them all different. And then be very specific at the point where you throw, and very specific at the point where you catch. Now, there's another piece to this, which is very little known, which is that you should always, when you're doing this kind of thing, let unit testing expand your contract. So this is a beautiful thing. You're unit testing something, and your documentation says, if I give you X, this will happen. And it doesn't say what happens if you'll give you Y or Z. Back in the good old days, we had that notion of being undefined. And people built systems, and you have to operate systems within their hardware parameters. So if you put the wrong voltage on it, the behavior is undefined, right? You're not allowed to do that. But unit testing gives us this great opportunity to come back in there and say, we're going to make up a whole bunch of things that can go wrong at test time in our mind, and we're going to create separate tests for all of those when the only thing the user of the code could possibly do is abort, right? But we're going to create 700 different flavors of abort and different tests for them. And I see this one in the Clojure test suite all the time. It's really an excellent way to make tests less useful, is to add things that were never in the contract in the test suite. Another thing you can do is put your language semantics on the wire. This is actually the thing that inspired me to call this narcissistic design. It's my language semantics, but I'm going to put them on the wire. And so now it's your language semantics too, whether you like it or not. And we have a long history of putting type systems on the wire. And so we have DCOM, we have Corba, we have Java RMI, and you'll notice that the way that the internet was built was it was built by a consortium like one of these that established a type system for web communications because we had clear evidence that type systems scaled. I have two things you may not want to hear, particularly if you love static typing. You know what's web scale? The web. And you know what it is? Dynamically typed. Now, let me ask you this question. This may be a little bit hard to read. I guess you can read the words. This is the current snapshot of the TIOBE programming language index, running from number 1 C down through Java, C++, Objective-C, C#, Basic, Python, JavaScript, Transact SQL, Perl, Ruby. So you look through all those languages. The really cool thing about all these languages is that many of you probably have individuating opinions about these languages. If I told you I was going to pick one of these languages at random and you were going to have to use it for the rest of your life, you would care, right? You would have really strong opinions about this. Now, look at this slide. Data representation languages: Avro, Bison, CSV, Eden, Freshen, Hessian, Java, JSON, Cryo, Protobuf, Thrift, YAML, XML. I bet that there's not a single person in this room who has as many opinions about the differences between these data languages as we have differences of opinion about the programming languages. I would argue. Now, here's the question. Which one of these affects the reuse and interop capability of your system once it's non-trivial in size? Which one of these things gets shared over the wire? These languages or the programming languages? These are the ones that get shared. And we got to keep attention away from that, people. We got to keep things where they are. So keep it complex, keep the focus on programming languages, let programming languages drive serialization. Your criterion for picking your serialization approach should be whatever's easiest from my language. Should always, always, always be that. Now, unfortunately, something came along as a kind of a wrecking ball of simplicity that really is messing up our ability to complicate serialization. And this is really hurting us because things are not as complicated as they used to be, thanks to JSON. So what are we going to do about this? I mean, this is an incredibly Spartan format. It is truly simple. It does very little, and it gets out of your way. And so we're going to have to find a different way to attack JSON if we want to make it complicated for people. We can't use the tried and true techniques of just letting language semantics float around. And we can actually go back to Einstein and say, everything should be made as simple as possible, but no simpler. We have to find ways in which JSON is too simple. And then we have to make sure that those insufficiencies in JSON don't just stop and end at some serialization layer, but they float through the entire application. There are a number of semantic insufficiencies in JSON because it's so simple. If you look at just this example here, you'll see that there's no distinct type for names, separate from strings. There's no distinct type for dates, separate from strings. And there's no distinct collection type for sets. There's only lists. The goal then is to make these impoverished semantics everybody's problem. Right? You don't want to solve this at the door. And the way that you do that is you have APIs that return actual JSON. Right? Have a goal of saying those problems float all the way up into your program, so you have to write your own date to my language date converter, and every other user of the API has to do their own conversion to get to the actual types that you want. This one's kind of subtle, and it's really quite common practice right now. So there's a real chance to say, you know what, we're really conforming with the way people do things by making our APIs actually return JSON. Now, write yourself a lot of unit tests. This is a great way to make your code more complicated. Uh-oh. I'm not going to touch the laptop again. So this is a unit test example written in RSpec, and it demonstrates the key features of example-based testing in general. It demonstrates that you have to do some setup. So I'm going to create a bowling object. That's what I'm testing. I have to specify some inputs. So when I rolled, I hit 0 pins. I have to specify some execution. I did that 20 times. And I have to specify some output. What happened after I did that? There was a bowling score. And I have to specify some validation. Now, all of those steps could be decoupled. All those steps could be decoupled. You could write a testing library that instead of working like traditional unit testing and spec-based libraries work, it actually separated out an explicit model behind the inputs. It separated out generation of inputs from programs. It separated out an execution engine that played through the inputs. It recorded the outputs in a database so that somebody could study them later, and performed generic property-based validation. There's some of this going on. There's people that are doing generative testing, people that are doing quick check and easy check. Do not do this. We want to keep our testing as complected as possible, right? So you want to be in the business of handcrafting inputs, because if you're handcrafting inputs, the computer can't do it for you, right? So if we want to have better testing, we're going to write twice as many tests. That's a job for a person. Also, embrace unit tests to the exclusion of everything else, right? Unit tests are useful. They're not intrinsically bad, but we can make them bad if we get rid of everything else. Unit tests are our documentation. Unit tests eliminate the need for code review. Another thing you can do is throw something shiny among the developers to keep them distracted. And that's what I mean when I talk about polishing up that English language DSL. Right? We already have something that's perfectly capable of setting up inputs and executing and recording outputs and validating, but we could spend hours and hours and hours coming up with a really good English language DSL. And the thing about it is, writing an English language DSL that a computer can usefully process is a research problem, right? If this were an actually solved problem, we'd write our programs in an English language DSL, not just our tests. So this is a fantastic time suck. Right? Just spend as much time as possible polishing that English language DSL. Now, I talked a little bit about, or I hinted at, the benefits of update in place for making complex systems when I talked about setter methods. But this really comes into its own when you think beyond the boundary of a process and move on into full system design. And the idea behind update information in place is pretty straightforward. The idea is that memory is expensive, right? You can buy a few kilobytes of it, but beyond that, you wouldn't want to pay for it. Storage is expensive. It's on these cassette reels. It's quite slow. Machines are precious, right? They're not ephemeral, throw them up, throw them down. They're these dedicated, expensive things that are in closets or rooms somewhere. And those resources are dedicated to you. And in a world where these things are true, then you would devise an update in place, or what I would call transient architectures, where everybody shares these transient things that are being updated in place. And these have wonderful characteristics if you want to build complex systems. They're difficult to share because they might be changing out from under you. They're difficult to distribute because that's just longer distance sharing. They're a catastrophe for concurrent access because they might be changing out from under you. Access pattern always has to be eager because it might change out from under you. Caching is a pain in the ass because it has to be kept coherent because the thing might be changing out from under you, and everybody's doing it. You win. You can use Java collections. You can use .NET collections. You can write a relational database. You can write with a NoSQL database, and you are already doing this. So keep on. Excellent, excellent work. Now, there are a few things to avoid. You may have heard people talking about persistent data structures. Persistent data structures are designed for a world where memory is available in megabytes and gigabytes, and machines are ephemeral, and storage is cheap. And so this really represents the world that has pertained for many years now. You should avoid these things like the plague. So under no circumstances should you use Clojure, or F# or Datomic, or the immutable collections portion of Scala. All that stuff, stay away from. Right? That is dangerously close to making your programs simple, so don't do it. And it's useful to remember what mutability is good for. If we don't have a use for mutability, we should write our programs purely functional. That would make them really simple. Again, we don't want to do that in this talk, but other people might. And so it's useful to ask, what does mutability get used for in software? And it really gets used for three things. It gets used to model the substrate on which we run because it is mutable. Fundamentally, right? There's actual RAM that changes underneath. Mutability gets used to implement specific algorithms that are designed to say this thing changes as part of this algorithm. And then mutability is used to implement a model of time. And an example of mutability being used to implement a model of time would be a Git repository. Right? So there, you have mutability, right? You can make more commits, but is Git update in place? Not unless you're doing some really wonky admin thing, right? So Git maintains the full history, or even multiple parallel histories, of things that have happened in your application. The good news for us as software developers is the reason that we do mutable OO has nothing to do with providing a time model, right? Nothing in OO, nothing in Java or C# as it's typically used, provides you a way to answer interesting time model questions, like what happened before what? What happened at the same time as what? What was the parent of this? What was the descendant of this? The reason we use mutability is almost entirely bullet point 1 here, which is we're just using it because it's what we have, right? It directly models the substrate we're running on. We need to keep doing that for as long as possible, right? This contributes more complexity to programs than anything else I've talked about today. So keep on keeping on. Finally, we need to leverage context in our systems. We leverage context all the time. In some sense, DSLs are a way of talking about leveraging context. When Neil Ford talks about DSLs, he always uses ordering coffee in American coffee shops as his example, where you can go in and speak this Baroque series of phrases which would have no meaning whatsoever as an English sentence, but because you're in the context of standing in Starbucks, you have an agreed upon context in which the two of you can speak. And the wonderful thing about leveraging context is it creates programs that require that context in order to run. The example that I'm going to pick to demonstrate this is the active record design pattern, and particularly as it's done in Ruby on Rails. So this is the picture that I got when I did a Google search for active record. This is the Martin Fowler patterns catalog picture of active record. And the great thing about this picture is that the line has no name. Not only does the line have no name, the cylinder that the line is pointing to has no name. Right? So what this is telling somebody, even just when you look at the very first picture, is that the names of the things in my model really matter, but the name of the table it lives in doesn't matter, and the name of the disk that table is on doesn't matter. And this propagates through to DSLs. So here is an example taken from the Ruby on Rails active record documentation. Song extends active record base. What table is song stored in? Well, it's not known here. It's known contextually. Where does that table live? What connection is that table made through? Well, you don't see that here either. It's known contextually. So imagine what happens if I need to talk to two databases. Well, as I said before, whenever anything like this comes up, just ignore everything and just go straight to Stack Overflow or equivalent to find out what's going on. So go and look on Stack Overflow, and it turns out that the DSL covers that. There's a little function called establish connection that you can use to say, oh, I want to be explicit right here. And in this particular case, the person was talking to an existing user database and a new user database, which is why they've called this old user. And so here they're going to connect to the legacy users database with their own connection and so on and so forth. So in one sense, I just want to say shame on the active record guys for actually providing an API. Because if they really wanted to make this complex, this would be impossible at this point. So they're kind of failing me. But there is still an opportunity for complexity here. So it turns out if you do this, then when you upgrade active record, it doesn't work anymore. And the reason that it doesn't work anymore is that the order in which things happen in setup matters and the order changed. Right? So there's some mutable, stateful way in which that DSL works under the covers. I should mention that. That's like a little sub-pattern under DSL. Make sure your DSL has a mutable imperative implementation underneath, not something that's functional and value-based. So there's the possibility of breaking your code around something you've never even seen before. And it turns out that when you want to go to doing more than one database, you have to actually go to your build tool, Rake, and do special things in your build tool to manage migrations. This is fantastic because now we're touching build tools as well. Notice I'm not writing code in Ruby anymore, or not entirely in Ruby. I'm writing code in another DSL, Rake, in order to do this job. Except sometimes that doesn't work either. This is all from Stack Overflow. And the problem with that is that depending on the way you call establish connection, not only have we messed up getting connected and messed up migrations, we've also messed up connection pooling. Now, I should say, everybody who's getting ready to tweet that I just pooped all over Active Record. Active Record's actually really good. It's one of the best examples of this pattern out there, and there are actually solutions to all these questions, and these things have actually been sorted out. But it got where it did by being a little bit DSL first, information model later, and that had to be backfilled in. So that was a little bit of complexity. And the way in which things break has to do with things being mutably assembled. The next level maneuver, you've now got the building blocks. The next level maneuver is to combine them, to do a bunch of them all at once. And I have hundreds of examples, but two really, really jumped out at me. And so I'm going to share with you my current candidates for Hall of Fame level complexity in programming. And that's object relational managers or mappers and build tools. So ORMs are they're almost a slam dunk. Right? They have setters, they prefer API to data, they prefer DSLs to API. Typically they're always connected. They make new abstractions for information, that's their whole job. They sometimes use static typing. They do update and place all over the place and then try to map that back to transactional semantics. And to make things convenient for developers, they leverage context. By all means, use ORMs everywhere you can. And then build tools. Build tools are a really intriguing example. Build tools are remarkably complex. You can read through some of the characteristics that they end up having here. But they're really also a statement about who we are as developers. Because, in fact, it's interesting. ORMs and build tools are both things that were primarily designed by developers with who as stakeholders? Developers. This gives me a queasy feeling in my stomach. Because one of the things I like to do as a consultant is say, my stakeholders are terrible, and they're always forcing these bad things on me. And they're forcing me into these paths of complexity, and they're always, never giving me time to finish polishing my English language DSL for testing and that sort of thing. But look what we get when we're left to our own devices. Right? These are the things we build when we are the stakeholders. And not only are we the stakeholders, but we're very, what I would call free time agile. Right? Free time agile is I have a little bit of free time, and so I can only ever very incrementally improve things. I can never sit down and spend the time to design. And free time agile is a really tough way to make things simple, but it's a great way to make things that are complicated. So these, but you can find others, right? You can take your own problem and say, how can I mix and match these and put them together in such a way that the system is going to be more complicated and that the complexity flows not just from me, but to other places. One good way to summarize that flow of complexity is increasing the requirements for coordination. Right? Making conversations stateful, making it required to get back to me to be able to do things, having single sources of truth. And all these things go together. Setters and update in place take you right there. Right? The minute you have something that's updated in place, you have to go to the place. Right? There's no possible way to get around that. So this is really, it's putting it all together. And the great thing about it is anybody going to get fired for doing all the stuff I just said? If your test suite passes, you can do all this stuff and just make this expanding thing with tendrils of complexity that goes and goes and goes, and then it turns to concrete in the system. And once that thing turns to concrete, you will never be out of a job. So I'd like to thank you. I've left, I believe, 7 or 8 minutes for questions before we break.